Welcome to part 2 of week 6, and in this second part of the narrated slides, I'm going to be talking about smaller, more appropriate scale technologies that we can use for delivering water and for water purification. And we're going to talk about some of the benefits and the risks. So first of all, the reason we want to do this is because we want to have this discussion is because small technologies are often overlooked because they're not the standard operating procedure right now. In a country such as the United States, where big projects are easy to implement, then it just seems like we would try to do those same sort of large projects everywhere. But it could be that in other areas other areas of the world, and in fact in areas around the United States, we should be looking at smaller environmental projects. And a couple of these are technologies for water supply and purification. So one of the reasons we're interested in lower impact, smaller technologies is because they have a lower impact because the technology is designed just to meet a particular need. So you can take innovative devices and approaches. You can address the specific institutional needs in order to support the implementation of those projects, such as, will this be accepted by the local users? Is it an acceptable technology for how they want to do things? It's important not to forget that. And then we can use targeted information technologies and educational support to train the people that need to use it. And finally, with small, flexible technologies, there's the benefit they're adaptive. We can change around the particulars to meet the very specific purpose and therefore have fewer side effects and less of a detrimental impact. Now that's the goal. Obviously, we could do it all wrong and have more detrimental impact from a bunch of bad projects. So let's look at some examples relating to water. And I'm going to talk about water delivery as an important piece here, and small-scale projects that help water delivery. Now, one of the sites that you may associate with sort of the Old West are these windmills. But these windmills are still in operation, and the reason is they're very inefficient, but they're super rugged. These can withstand all sorts of wind problems out in the prairies of the United States, Australia, other places where they're implemented. They're easy to fix because they're all mechanical, and all they do is pump water from relatively shallow groundwater wells up to water stock, or maybe provides water for a small agriculture operation. And they're just made out of very durable and easily fixed projects. So something as sort of old school as these windmills is actually a very valuable thing to consider in terms of pumping water. If you go out in the middle of the prairie someplace and it's really windy and dusty, and you put in a high-tech wind generation facility, you're going to have to maintain it and get out there to fix it all the time. That's just looking for trouble. So again, don't ignore some of these old school technologies. Another example here to illustrate how we might use a combination of equipment to meet different needs. Here's the general schematic for what it would take to have solar panels going through a voltage controller to a pump and a storage, and then distribution to home or fields. And we can size each one of these independently to meet the exact needs we have. So for example, for distribution of homes, of drinking water, we want to have a large tank. We're probably going to have more solar panels just because we're going to pump from a deeper well. But we need a large tank in order to be able to last over the dry period in some of these countries. But for drip irrigation, we might have a shallow well, which would require much smaller solar panels, and we're only going to drip irrigate for a period of time when there's water available to drip irrigate, and so we can have a much smaller panels, pump, and storage tank. And so just for example, on here, a large-scale community potable water, you might need 1,000 gallons to distribute to 40 homes, but for a small-scale drip irrigation for an acre might only need a 100-gallon storage tank. So these are very different sort of project goals, and it shows the flexibility of scaling the solar panels, the pump, and the storage all to the very specific purpose. Now another example is to deliver water is from Paul Pollock's work, where he started out by saying, well, the reason his statement was the reason people are poor is they just don't make enough money, and one of the ways they could make more money was to be able to deliver water to their agricultural fields. In a lot of cases, they were stuck carrying buckets of water, or they had to carry water, and so he devised a couple systems that were easy. One is this, diesel, small diesel pump that would take like a lot of effort to get there and maintain. But actually, one of the appropriate scale technologies that he developed and sold to people were these treadle pumps. It's a little hard to see in this picture, but a treadle pump is like 2 cylinders, and people stand on the levers that control these pumps, and just by moving their legs up and down, they pump water, and they can irrigate about an acre. An individual can irrigate about an acre, and then get money from selling the crops, and use that to pay off the loan they took to buy these relatively inexpensive treadle pumps. So Paul Pollock's whole approach was, reason people are poor, they don't make enough money. What do they need to make money? They need some simple technology like this, a treadle pump, and they make money. Other ones are a little bit more complicated, like this solar array. This would be good for a larger farm, and they got to come up with quite a bit of money to get it set up in the first place. But again, these sorts of projects are aimed at rural agriculture where there's some sort of water available, but it needs to be either recovered from a well and put on the crops, or a shallow well and distributed. Another example of this same approach was some work that I did in Nicaragua, and the purpose of this study was to provide better information on renewable energy, water resources, and watershed health. Those 3 things, and provide that information to the rural farmers and the local businesses in the town, so that those 2 sides could get together, and farmers could buy the appropriate solar equipment, and the town business people would be able to understand what solar equipment might be useful to farmers. So the idea was to provide the information background that in the United States would just be, we could just look it up. But in Nicaragua, they just don't really have that sort of micro-scale information available. So we collected weather data that was localized to very specific watersheds. And again, 2 watersheds, one facing east and one facing south, would have very different water demands and water availability. So it's a very local information that you need. And then to help them understand watershed health, so we surveyed the watersheds looking for small streams that might have seasonal water, small streams that might indicate subsurface water, and then connected that with references on how they could use that for solar drip irrigation or other projects. So the idea here was to provide information capital so that there could be this sort of, so that local entrepreneurism could take off. Without that basis of the information, they'd have a hard time making those first commercial steps in order to make it profitable for both sides. Now, these small examples relating to water also, I want to go back to the example from the Niger, where the people in the Niger have been using, again, here's a treadle pump with a whole bunch of people having fun pumping local water. And in the Niger, incredibly dry area, and here's the Sahara Desert. Down here's Nigeria. This area that they were able to, through local communities, pumping water and growing trees to help shade their agricultural areas. You can see just from those small-scale efforts over this area. Here's before 1975. Here's after that. So there's ecosystem restoration going on. Each little black dot is a clump of trees. You see there's actually more trees because the people are using the land in an appropriate method with these small-scale pumps and small-scale farms. They're actually improving the quality of the land. All right, so that's an example. Those are several examples of how these small-scale water production can help the economy, but also the ecology of an area. Now, I want to give one quick example of water purification. And the problem with water purification is many people around the world, several billion, don't have access to clean water, and what they'll often use as a way to clean that water up is boiling. When they do that, that leads to deforestation and devegetation of their local areas. They find wood or twigs to boil the water. So they either have the choice of boiling the water and deforesting their local watershed, or risk getting sick. So one of the innovative solutions, and this is coming out of a lab at Portland State called the Sweet Lab, is to create these technologies that purifies the water without firewood. And to get funding to help support that, you need to verify that people are actually using that. So the Sweet Lab has developed a set of sensors, and here's a picture of some of the sensors, and these are attached to water purification systems, and they log how much water is being used. And so the people have to pay, the customers have to pay for the water purification system, so they buy that. But what happens is that the overall funding for this project is paid for by carbon offsets. So we talked about the last week. And the reason this can work is because they can verify how much water was being purified with these purification filters. That equates to so many tons of wood not being used to purify water by boiling, and that's the basis for the offset funding. So it's, instead of burning trees, they use these filters, and then that allows them to get some funding from carbon offset people who want to offset their carbon excesses and help fund this project. So this is a very innovative way to get money to help purify water and at the same time help the environment by reducing deforestation. Okay, now one of the risks of small-scale projects is that because it's small-scale, it's sort of like having all your eggs in one basket. If you have a big waterworks project and you have a drought in one little part of the watershed, or less water in one part of the watershed, then the other part of the watershed makes up for it. Or if you have ways to pump water between different parts, like we saw in California and China, you can balance the water deficit in one area and make up for it with water excess in the other area. However, if you are running a small watershed or water collection system, so for example, collecting rainwater off your roof, then you're really susceptible to a local drought is the extent of your system. So here's an example of the water year in Oregon, and in June we might get 1.69 inches, July 0.6 inches, August 0.7 inches of rain. So during this period of time from June, July, and August and into September, there's very little water that comes in that can be collected off the roof. So you would have to collect water to make it through that period if you were going to rely solely on roof rainwater collection. Now, the probability of these periods of drought is, this is the average over a long period of time, but there's been times when there's been 44 or 51 days without rain at all, and then maybe just a little bit of rain. And again, to account for that, you would have to have a very large storage tank in order to collect the rain off your roof from late spring and have that carry all the way through the summer. So the way you would calculate that is how much water do you need? Well, there's the water efficiency of the crop, like we saw last week, and the dependence on temperature and humidity. I'm going to come back to that in just a second. And you would calculate how much water you could collect. Here's your roof, the area of your roof, and collect it, and here's how much storage you have. So you would calculate how much water you need for your crop per day, per square meter of your garden. Then here's how much water you could collect, and you'd figure out how big a tank you needed and how much water you would be able to store. Well, the problem with this and with other environmental problems is that we need to take into account the interdependent risks. Just I mentioned in section 1 of this lecture about how the risk of the cooling tower failure was probably independent from the ecosystem stresses. Well, this is the same problem, that as we have the length of drought, it's probably more severe. And that as you have more severe a drought, you're going to need more water required per day per plant. So you've got to change as you try to account for a longer drought. You also need to account for that the longer drought's probably more severe, hotter and drier, and it's going to require more water use per plant. So the amount of water you're going to need to store is going up rapidly as you try to account for the probability of a longer drought. And this type of interdependent risk is what leads to some major failures. A good book on this is The Black Swan by Nassim Taleb, and he talks about risks that people thought were independent, so you could just multiply the two risks by each other and you find out, well, it's really diminishing. But if the risks are actually interdependent and you don't expect that, then the potential impact could be dramatic and much higher than you expect. And so in order to account for that, you need to really look for these sorts of interdependent risk factors. All right. Thank you, and I'll start up part 3 in just a second.